Welcome to the deep dive. Our mission, as always, is to make sure you walk away with, the critical context and maybe the most surprising bits from the latest research.
And today, we've got something really special.
Yeah, today we're hopping into what feels like the ultimate time machine. A 6 million-year-old chunk of ice. Seriously.
It really is an unprecedented scientific win. I mean, scientists have actually recovered the world's oldest directly dated ice, and crucially, the air trapped inside it from Antarctica.
Wow.
And this doesn't just push the climate record back further than we thought possible. It genuinely changes our understanding of what ice core science can even achieve.
That's got to be the ultimate source material for climate history, right? So our deep dive today is focused on these findings from the Center for Oldest Ice Exploration. That's the COLDEX team. We're going to try and unpack the secrets trapped in this ancient ice. We'll connect them to the Mid-Piacenzian warm period, which is, well, a really key analog for our own future climate.
Absolutely critical.
And maybe most importantly, explore these, frankly, shocking oceanic temperature thresholds, the tipping points that seem to commit our massive ice sheets to, well, catastrophic sea level rise over the long term.
Yeah, we're not just looking back at history here. We're talking about defining the actual thermal triggers, the tipping points that could decide the fate of coastlines globally.
Okay, let's start with the discovery itself, because for decades, the sort of gold standard continuous ice core record, the one everyone used, it only went back about 800,000 years.
That's right. And teams all over the world were aiming, maybe hoping, to find ice that could push that to 1.5 million, perhaps 3 million years, if they were really lucky.
So a big jump that's still...
Exactly. But then this discovery from the COLDEX team just completely shattered that timeline. They were working in the Allan Hills blue ice region of East Antarctica.
Okay.
And they found ice layers dating back more than 6 million years.
Okay.
It's an archive of climate data from an era we previously had basically no direct atmospheric insight into.
No. 6 million. And the way they found it is interesting too, right? Because they didn't drill the usual 2 or 3 kilometers down, which is what you normally need for those deep, continuous cores.
No, not at all. They drilled relatively shallow holes, only about 100 to 200 meters deep, near the edges of the main ice sheet.
How does that even work? How does 6 million-year-old ice end up so near the surface?
Well, that's down to the really unique geology and conditions in the Allan Hills area. You have to picture this rugged, mountainous terrain right near the edge of the ice sheet.
Okay, got it.
Now, combine that topography with these incredibly strong, extremely cold winds. So they're called katabatic winds.
Katabatic winds, right.
These winds are so powerful and consistent, they actually slow the natural ice flow down almost to a complete standstill in certain spots.
So the usual process where ice flows downhill and buries the older layers deep down, that gets like short-circuited.
Precisely. Those winds literally blow away most of the fresh snow that would normally accumulate year after year. So instead of getting buried deeper and deeper, the older ice gets compressed and sort of jostled back up towards the surface near those mountains. It preserves these ancient layers where we can actually get at them.
It sounds like an incredibly tough place to work, though.
Oh, it is. Bitterly cold, windy, extremely challenging for field work. But it's one of the very few places on Earth where you can find this kind of ancient ice so close to the surface.
And then there's the dating. You mentioned it's directly dated. That sounds like a big deal technically.
It is. It's a major technical achievement. That's why we can say with such confidence this is the oldest directly dated ice. They call the technique direct dating.
Okay, so how does direct dating work compared to other methods?
Well, traditionally, you might infer age based on, say, dating volcanic ash layers above or below the ice, or by matching patterns to known climate cycles, which gets less certain the further back you go.
Right, more inference involved.
Exactly. But with direct dating, they're reading the atmospheric timestamp directly from the ice. They measured a specific isotope of argon, a noble gas, that was trapped inside the tiny air bubbles within the ice itself, from when the ice first formed.
So you're literally analyzing the composition of the air that the Earth was breathing, so to speak, 6 million years ago.
That's exactly it. See, argon-40 is produced by the natural radioactive decay of potassium-40, which is found in rocks.
Okay.
As that potassium decays over millennia, the argon-40 gas is released into the atmosphere, and some of it gets trapped in those air bubbles as snow compresses into ice. By measuring the amount of argon-40 in a bubble,
you can calculate how long it's been trapped there.
Precisely. You measure the ratio of the decay product, and that tells you the age of the air and therefore the age of the ice surrounding it with much greater precision than older methods allowed for this kind of discontinuous ice.
Yeah.
It lets them build what they call a library of climate snapshots.
A library of climate snapshots. I like that. So, okay, they have this 6 million-year archive. What's the first big headline finding they pulled out, temperature-wise?
Well, the initial analysis focusing on oxygen isotopes locked in the ice, which act as a kind of thermometer.
Right, the standard proxy.
Exactly. That revealed this really massive but very gradual long-term cooling trend in that specific Allan Hills area. They found that over the last 6 million years, the region cooled by about 12 degrees Celsius.
12 degrees C. That's huge. That's about 22 degrees Fahrenheit.
It is huge. And this is the first direct quantitative measure we have of this long-term Antarctic cooling trend over that vast time scale.
12 degrees of cooling, but spread over 6 million years. I mean, that really underscores the incredibly slow pace of major geological climate shifts, doesn't it?
It certainly does. It sets a kind of baseline for the Earth's natural thermostat changes.
Okay, so now that we have that huge timescale established, let's zoom in. Let's focus on a specific moment within that 6 million year record that scientists keep pointing to as a kind of mirror, or maybe a warning, for our own future. That's the Mid-Piacenzian warm period, the MPWP.
Yes, the MPWP. It's roughly dated between 3.3 and 3.0 million years ago. And you're right, it's widely considered probably the most critical analog period we have for understanding potential future climate scenarios.
Why that period specifically? What makes it such a good analog?
Well, two main things. First, the Earth systems, things like ocean circulation and continental positions, were broadly similar to today, though not identical. But second, and crucially, the atmospheric chemistry, specifically CO2 levels, were eerily similar to where we are now.
Okay, walk us through the conditions back then. How warm was it? What were the CO2 levels?
So global average temperatures are estimated to have been about 2 to 3 degrees Celsius higher than pre-industrial levels, maybe slightly more.
2 to 3 degrees warmer overall.
Yes. And the really key part, atmospheric CO2 concentrations. The estimates generally fall between 330 and 450 parts per million by volume.
And we just recently passed, what, 420 ppm?
Exactly. We're right in that Piacenzian range now, or even slightly above the lower end of it. That similarity in the key greenhouse gas is precisely why the MPWP is studied so intensely. It's our best look at how the Earth system, especially ice sheets, responded to CO2 levels like today's, given enough time to equilibrate.
And presumably, like today, the warming wasn't spread evenly across the planet back then either. You mentioned polar amplification earlier.
Oh, absolutely. The evidence points to enormous polar amplification during the Piacenzian. The poles warmed much, much more than the global average.
Like how much more?
Well, some studies cited in our sources show, for example, that eastern interior Alaska might have been something like 7 to 9 degrees Celsius warmer year-round than it is today. Huge difference.
Wow. Okay. And when you have that much warmth, especially at the poles, the big question becomes sea level, right? What happened to the ice sheets?
Precisely. And that's where, for a long time, there was a significant debate, maybe even a controversy. How much higher was global sea level during the peak of the MPWP?
What did the geological clues suggest, like evidence from old coastlines?
The earlier reconstructions, the ones based on things like ancient shorelines found inland, or the elevation of certain cave formations that only form at sea level, they often suggested a peak sea level that was, well, towering. The most commonly cited figure was probably around 22 meters higher than today, plus or minus about 5 meters.
22 meters. That's almost unimaginable. That would redraw coastlines completely. Major cities gone.
Completely. It's a catastrophic amount of sea level rise, and figuring out where all that water came from was the challenge.
Yeah, how do you even get 22 meters? Where does the ice loss come from?
Okay, let's break it down. To get that high, you basically need 3 major ice reservoirs to melt significantly. First, you assume the complete loss of the Greenland ice sheet.
Okay, that's about 7 meters of sea level equivalent, right?
Roughly, yes.
Yeah.
About 7 meters. Second, you need the complete collapse of the West Antarctic Ice Sheet, the WAIS. That's considered the most vulnerable part of Antarctica.
And WAIS adds about another 5 meters.
Around 5 meters, yeah. So Greenland plus WAIS gets you to about 12 meters total.
Okay, 12 meters. But the estimate was 22 meters. Where does the other 10 meters come from?
It had to come from the big one, the East Antarctic Ice Sheet, the EAS.
Which holds the vast majority of the world's ice, and we often think of it as pretty stable.
Mostly stable, yes, but it's not monolithic. To get that extra 10 meters, you'd need significant melting from the low-lying, marine-based coastal sections of the EAI as parts of it that, like WAIS, are grounded below sea level. places like the Wilkes Basin.
So even the stable giant had vulnerable parts that contributed. But I gather that 22-meter number has been revisited.
It has, yes. Over the last decade or so, more sophisticated geodynamic modeling has changed the picture somewhat.
Geodynamic modeling, what does that account for?
It accounts for how the solid Earth itself responds when you remove the immense weight of an ice sheet. It's called lithospheric rebound, or glacial isostatic adjustment. Basically, the Earth's crust slowly springs back up once the ice load is gone.
Ah, so the old shorelines might have bounced up higher than the actual sea level was at the time.
Exactly. Accounting for that crustal movement led to revised global sea level estimates for the Pliocene peak. The newer consensus tends to put the figure lower, maybe closer to 16.0 to 17.5 meters above present.
16 to 17 meters, I mean, still catastrophic, absolutely devastating, but significantly less than 22.
Right. And that lower number is actually crucial because it aligns much better with what state-of-the-art ice sheet models suggest is plausible for Antarctic melt during that period.
Yeah.
Those models generally struggle to get much more than, say, 10 meters total out of Antarctica, even under sustained warmth.
Okay, so the geology and the physics are starting to match up better around that 16, 17-meter mark.
It does seem to reconcile things better. And it shifts the focus. The question becomes less about, could it have been 22 meters? And more about, okay, what specific thermal conditions, what ocean warming thresholds had to be crossed to cause that 16 or 17-meter rise, starting from ice sheets roughly like today's?
Right. Which brings us neatly to those ice sheet modeling studies you mentioned, the ones using Pliocene climate scenarios to figure out those thresholds. What did they find? Where are the tipping points?
Well, the models consistently show that the marine base sections of the ice sheets are exquisitely sensitive to ocean warming,
Yeah.
particularly the West Antarctic Ice Sheet, the way ice.
Because it sits mostly on bedrock that's below sea level.
Exactly. That makes it highly vulnerable to a process called marine ice sheet instability, or NESI.
Okay, can we just quickly define NESI? What happens there?
Sure. So imagine the edge of the ice sheet resting on the seabed. That's the grounding line. If warm ocean water gets underneath and melts the base, the grounding line starts to retreat inland. Now, with waves, much of the bedrock slips downward as you go inland. So as the grounding line retreats into deeper water, it exposes an ever taller cliff face of ice to the warm ocean.
Ah, so more surface area for melting.
Yes, and potentially faster flow. It creates a positive feedback loop. Retreat leads to faster retreat. It becomes self-sustaining once triggered. And the model suggests this waves collapse, driven by Missy, can be triggered by surprisingly little ocean warming.
How little?
The tipping point seems to be at an oceanic warming of just 0.5 Kelvin above present-day levels, if regional snowfall also drops below about 80% of current rates.
Half a Kelvin. That's the same as half a degree Celsius. Just half a degree change in the ocean temperature near waves could potentially commit it to collapse, assuming less snow.
That's what these models indicate, yes. And they also show that if the ocean warming near waves reaches 1 Kelvin, or 1 degree Celsius,
Then it collapses anyway.
then the collapse happens in the models, regardless of the precipitation rate. The ocean warmth just overwhelms everything else. Waves is definitely the low-hanging fruit when it comes to ice sheet instability.
And if only waste collapses, how much sea level rise does that represent in these models?
The models show a contribution of between 2.7 and 7.0 meters of sea level equivalent just from waste collapse, depending on the specific model physics and scenario.
Okay, 2.7 to 7 meters is still enormous, but it doesn't get us to the 16 or 17 meters needed for the Pliocene.
No, it doesn't. To reach those higher Pliocene sea levels, you absolutely need major contributions from the vulnerable marine basins within the East Antarctic Ice Sheet as well.
Right, you mentioned the Wilkes Basin and the Totten Glacier region earlier.
Right.
Are they as sensitive as waves?
No, they seem to have significantly higher thresholds, which makes sense. They're generally colder and perhaps configured slightly differently. For the Wilkes Basin, the model suggests retreat really kicks in only when the nearby oceanic warming reaches about 3 Kelvin or 3 degrees Celsius above present levels.
3 Kelvin? Okay, that's a much higher barrier than the half a degree for waves. Makes sense. And the Totten Glacier area.
That requires even more ocean warming according to these simulations. You need an anomaly of at least 4 Kelvin, 4 degrees Celsius, to really initiate significant retreat there.
So there's a clear hierarchy of vulnerability then. Waste goes first, relatively easily. Then Wilkes Basin needs substantially more warming. Then Totten needs even more.
That's the sequence the models point to, yes. a stepwise series of thresholds being crossed.
But I think I saw something in the notes about a potential mitigating factor, something that could push back against the melt, especially for Wilkes. Precipitation.
Yes, that's a really important variable and a complex one. While warmer oceans drive melt from below, a warmer atmosphere can also hold more moisture, potentially leading to more snowfall over Antarctica.
Ah, so more snow piling on top could counteract the melting at the base.
Potentially, yes. The models show that very high precipitation rates in some simulations, up to 3 times present-day snowfall, could potentially slow down, or maybe even hamper, the retreat of the Wilkes Basin, even if the ocean temperatures get above that 3 Kelvin threshold.
So it becomes a battle between ocean melt underneath and snow accumulation on top.
Exactly. It's a dynamic balance, and predicting future precipitation changes accurately is still a major challenge.
Okay, one more mechanism question. There's been a lot of discussion, maybe controversy, about something called marine ice cliff instability, or MICI. This is the idea that really tall ice cliffs at the ocean edge might just mechanically shatter and collapse very rapidly. Was that needed in these models to explain the Pliocene melt?
That's a great question because MICI is a hypothesized process that could lead to much faster retreat than MSI alone.
Right, sounds pretty dramatic.
It does. But interestingly, the model results we're discussing here suggest that MICI is not actually required to explain the large-scale collapse of, say, the Wilkes Basin during the Pliocene. Yeah, they found that high oceanic temperatures causing strong melt at the grounding line were sufficient on their own to initiate and sustain the retreat needed to match the Pliocene sea levels, even without explicitly including that rapid cliff collapse mechanism in the model physics.
So basically just cooking the ice from below with enough warm water is enough to do the job, even without invoking the extra drama of shattering cliffs.
That seems to be the implication of these particular studies, yes. The ocean warmth is the primary driver.
Okay, let's try and pull all these threads together. We started with this incredible discovery of 6-million-year-old ice, showing a very slow, gradual 12 degrees Celsius cooling trend over geological time.
A snail's pace, really, in Earth history terms.
Yeah. But then we zoom into the Pliocene, 3 million years ago, with CO2 levels like today's, and we see geological evidence for maybe 16, 17 meters of sea level rise.
A vastly different world state triggered by similar CO2.
And now, these modern modeling studies trying to replicate that show these incredibly sensitive near-term tipping points, especially for West Antarctica, potentially triggered by just half a degree of ocean warming.
A tiny nudge compared to the long-term geological changes.
So what does this deep dive ultimately tell us about our commitment to future sea level based on where we are now?
Well, it strongly reinforces the core idea. Reaching those really high sea level stands, seen in past warm periods like the Piacenzian, absolutely required crossing multiple major Antarctic tipping points, probably in sequence. Waves likely went first, followed by significant retreat in the EAI's marine basins like Wilkes.
And the models suggest that under those Pliocene-like conditions, but starting from today's ice sheet configuration, the total Antarctic contribution could be somewhere in the range of 2.7 to maybe 8.9 meters of sea level rise.
That's the range simulated across the ensemble of models, yes, covering just waves collapse at the low end, up to significant EAI's contribution at the high end.
Now, we should be clear, right? Even if we cross these thresholds, that full amount of sea level rise wouldn't happen overnight. It would take centuries, maybe millennia, for the ice sheets to fully retreat and reach a new, smaller equilibrium.
Absolutely. Ice sheets respond relatively slowly, over hundreds to thousands of years. But the crucial point from the Pliocene analog is the commitment. It shows that atmospheric CO2 concentrations, similar to today's, if sustained, likely commit the planet's ice sheets to eventually contributing enough melt for a drastically higher sea level.
The inertia is huge, but the destination seems kind of baked in once you cross the threshold.
That's the concern, yes. The contrast is just so stark. We measure the slow, natural cooling over the last 6 million years, that 12 degrees Celsius and, well, millions of years.
Geological time.
Right. But the physics of instability for the West Antarctic ice sheet, according to these models, operates on a threshold of maybe half a degree of ocean warming. Compared to the geological record, that's practically instantaneous.
So here's maybe the final thought to leave folks with. We have this direct measurement from the 6-million-year-old ice showing just how slowly the Earth system can change 12 degrees over millions of years. And yet we now understand that the immediate vulnerability of a huge chunk of Antarctica, the Wadons, seems to be triggered by a temperature change measured in just fractions of a degree, the threshold we might be approaching or may have already crossed in some regions.
It's a disturbing juxtaposition.
Yeah. What does that incredible contrast between the slow geological past and the hypersensitive present suggest about the timescale of potentially irreversible change we might be facing right now? It's not just about how much sea level will rise eventually, but how quickly we might be locking in that future. Something to think about.
Indeed. The ice archive might be ancient, but the warning it holds feels incredibly immediate.
Well, thank you for guiding us through this complex, fascinating, and frankly, pretty sobering deep dive into ancient ice and modern tipping
It
points.
was my pleasure. A lot to process there.